So welcome to Tech Talk, everyone. We are delighted to have our friend and colleague from the Medical University of South Carolina, Paul Nietert, giving us a talk on constrained randomization. So before I introduce him, let me mention some housekeeping issues. First, make sure that you sign in and please RSVP so that we can better prepare for the next session. Online participants, please keep the mics muted unless asking a question and keep the video turned off. Use the chat feature in BlueJeans if you have technical questions. Make sure that you subscribe to the series to learn about upcoming tech talks. You must subscribe separately from the ID series. Next month, we have medication analysis, how exclusive breastfeeding affects child obesity at age 4 by Pan Wu from the Value Institute here at Christiana. You can see the full schedule on the ACCEL website, and all the previous presentations are available on our website, DE-CTR.org. I'm really delighted to introduce, and also, before I forget, for everyone in the room, if you have any questions, please raise your hand because Sartre is going to mute the room. So, if you have any questions during the talk, raise your hand. So I'm delighted to introduce Paul Nietert. Paul is Professor of Biostatistics and Epidemiology in the Department of Public Health Sciences at the Medical University of South Carolina, and also Program Director of the CTSA Biostatistics Core. He has a PhD in Biometry and Epidemiology from Medical University of South Carolina, and a Bachelor of Science in Mathematics from Duke. He's currently the PI of the Methodology Core for a Center grant funded by the National Institute on Arthritis and Musculoskeletal Conditions, and he is and has been co-investigator on numerous and very impressive number of AHRQ and NIH grants. He has had multiple awards, almost 200 peer-reviewed publications, and has mentored many students. Thank you so much, Paul, and we are very excited about this subject.
Well, thank you very much for having me today. If somebody does need to ask a question along the way, that would be great. However, I don't know that I will see whether you have a question or not. So I think Sarah Faye may need to interrupt if somebody wants to ask a question. But if I don't answer your question along the way, we'll have plenty of time at the end to address any questions. So bear with me. This is my first webinar, so if I'm getting a little off track along the way, just forgive me. So this topic about constrained randomization came up in some of the work I was doing a little while ago, and I realized it has specific applications to group randomized trials. And although I did this back in 2008 and 2009, I think it's still very relevant today. It seems like group randomized trials are becoming more and more popular, especially within funding agencies like PCORI. And so I do not have any conflicts of interest to disclose. And what I thought today is I'd just give a little bit of a review about randomization. You think randomization is a very straightforward process, but the more you look into it, the more complicated it can become. And then I want to give you a little overview about some of the similarities and differences between what I'm calling traditional randomized controlled trials and group randomized trials. And then I would like to present a simple algorithm for helping to balance groups within a group randomized trial. And I'll explain what I mean by balancing. And then I'll discuss some limitations and some future directions. So first question, why do we randomize in a randomized trial? Well, there's several reasons, and I pulled some of this information from a few different references, and I've listed them along the bottom. And so one of the main reasons is just to help assure everyone of impartiality. It also helps provide a basis for statistical inference. It helps ensure that any differences at the end of the study are primarily due to the treatment or the group assignment. It also provides a convenient means of just implementing the treatment assignment. And perhaps one of the most important things a reason for randomization is it helps eliminate selection bias. So essentially, randomization helps ensure that there are no systematic differences between the groups at the beginning with respect to measured and unmeasured confounders. And so this kind of goes back to the point I made earlier, in the end, randomization helps us, by eliminating selection bias, it helps us determine that whatever differences we see at the end are due to the treatment assignment or the group assignment and not due to other measured or unmeasured factors. So there are different types of randomization strategies. So we can talk about simple randomization, random permuted blocks. We have stratified randomization, adaptive randomization, biased coin randomization. And basically anything other than simple randomization, I would just call constrained randomization. In other words, it's randomization with some form of constraint put upon the different ways we could randomize our subjects, and we do that for a number of reasons. So what do we mean by simple randomization? Essentially what we're saying is we just toss a coin. If it's heads, they go in the intervention group. If it's tails, they go in the control group. Or we could generate a random integer greater than 0. And if it's an even number, we could put them in the intervention group. And an odd number, we would put them in the control group. And so that's essentially what simple randomization is. And the only con to this, well, there's probably other cons as well, but one con is that in the end, there's no guarantee of equal numbers of subjects in the intervention and control groups. And I'll go ahead and just stop here not stop here, but I want to give you a little story. Don't ever assume when you're working with colleagues that they know exactly what randomization means. I recently had an experience with on a project I was working on, and the person who I had assumed knew what randomization was ended up just kind of picking. They actually looked at the study subject and decided whether they thought they should go in the treatment or control group, and it was basically a disaster, and we had to stop the study. So always, as biostatisticians, we're often in charge of randomization, but be careful about what you assume. The people who will be who will actually do the treatment assignment, you need to make sure that they understand what randomization means and how the process occurs. So we have also something called random permuted blocks. That's another type of randomization. So for example, if we have blocks of size 4, after every 4 patients, then that would force there to be an equal number of subjects in each group. So for example, block 1 might be A, B, A, B, meaning that the first person goes into treatment group A, the second subject goes into treatment group B, and so on. And so what you can see is at the end of each block, you would have equal numbers in each group. Now, one downside to this is after 3 subjects have been enrolled, if somebody is thinking about this, they could actually predict with certainty then what the 4th subject, which group the 4th subject would be randomized to. So there is a downside to using just block sizes that are all the same. So one thing we do to avoid that is by changing the block sizes along the way. So you might have a random block size of 4, then maybe 2, then maybe 6. And that way it's a lot harder for anybody to determine, to be able to kind of break your blind in terms of the randomization process. So stratified randomization is something that a lot of clinical investigators will like to do. And essentially what you're trying to do here is you want to ensure that the treatment group allocation is balanced within strata. So you might have one stratum, or you might have two. And so here's an example where I'm trying to think about stratifying the randomization based on gender and race. So in my hypothetical example here, I have, and I hope you can see my mouse, but I have a total of 150 subjects that I'm trying to randomize. There are 40 white males, 60 white females, 20 black males, and 30 black females. And what I'm trying to do is then randomize within each of these. So in this case, I have 4 strata, and I'm trying to allocate within strata so that I achieve balance. So what do I mean? So 40 white males, what I mean is that I'm going to assign within this strata 20 into a treatment group and 20 into a control group. And this type of randomization works fine when you have small numbers of strata. So once this with 2 strata here and 2 categories per strata, I have 4 total strata, 2 by 2. If you had a third strata with 2 categories, then you would have 8 strata. So anything more than 2 or 3 strata is going to oops. Sorry, that was my phone waking up. Anything more than 2 or 3 strata is going to get rather complicated. But one thing to realize here is that although we're balancing within these 4 strata, we're also by definition then forcing a balance on the margins. So later on I'm going to refer to marginal balance, and what I mean here by marginal balance is, for example, among all of the white subjects here, we have 50 in the treatment group and 50 in the control group, and among the 50 blacks, we have 25 in each group as well. And same thing goes for males and females. So we're balanced by gender, by race, and by the race-gender combination. So you've probably also heard of adaptive randomization. An adaptive randomization has to do with the treatment assignment, modifying the treatment assignment probabilities along the way. And these probabilities are basically modified based on departures from the desired allocation ratio. So if you're doing simple randomization and then along the way you have too many in the treatment group or too many in the control group, you could modify the probability of being assigned into one of those groups. There could also be differences in the function of baseline characteristics of the treatment groups or outcomes. So if in other words, we change the randomization process along the way to help deal with essentially the underlying validity of the design. And so again, we're doing this so we either to balance the 2 groups with respect to the sample size or their baseline characteristics or even their outcomes along the way. So there are some disadvantages to constrained approaches, and this is worth mentioning. Sometimes they can be logistically difficult to implement. So if, for example, I'll back up a minute, if you're recruiting subjects into a randomized trial along the way and you're incorporating their baseline characteristics or their outcomes into the randomization, then you would need to have probably a programs set up in advance so that when you do need to randomize the next subject, it can be done seamlessly. But setting those algorithms up can be challenging and have to be done upfront. So the constrained randomization, constrained approaches, as I mentioned, also it's possible to lead to unblinding, and it can also add some complexity to the analysis. So let's jump over to what we refer to as group randomized trials. So they're also referred to as cluster randomized trials. And essentially what we're doing is And I'm sure you've probably seen some of these mentioned in different contexts recently. But you're randomizing groups of subjects or clusters of subjects. This could be, I've seen this where people are randomizing schools, where you have one school gets an intervention, the other doesn't, or maybe classrooms within schools. Perhaps you're randomizing physician practices, so whole groups of practices, and your patients are your study subjects. Recently, actually, I was working on one yesterday where we were randomizing villages in India to receive an intervention, and the interventions in these cases can be at the level of the cluster or the group, and it's also possible for the intervention to be at the level of the subjects. But the important thing about all of these types of randomized trials where we're randomizing groups is that once you go down this road, that the subjects cannot be considered independent from one another. And because of this, your traditional data analysis is going to need to account for this. So we're going to need to either use some type of mixed effects models where we can include random group effects like random practice effects or random village effects, random school effects, or we'll use some kind of GEE models. So again, instead of something like a regression model or a logistic regression or even a chi-square t-test, you're going to have to use a more complicated approach. So let's see. Some other differences. In the traditional randomized trial, the unit of randomization is typically the unit of analysis. So in a cluster randomized trial, the unit of randomization is a cluster, and the unit analysis is often not the cluster. So in the example, what I mentioned, we were randomizing villages. The intervention was going to be an intervention to improve exclusive breastfeeding among pregnant or mothers, or that we were recruiting pregnant women, and we were going to be, after they delivered, they were going to be followed for 6 months to see if the intervention resulted in exclusive breastfeeding or not. And in that case, the unit of analysis is the mother-infant pair. But we were randomizing villages because we thought that there was a potential for intervention to some contamination to go on. And in other words, we thought that it was possible for the women within a village to be talking to each other about their breastfeeding and how that might impact their children. So there are a number of different reasons for doing group randomized trials. Sometimes you're trying to do an intervention where the intervention involves teaching physicians or nurses or the people who treat the study subjects. And this can be challenging in terms of getting an IRB approved, an IRB application approved, because you're exactly who your study subjects are is not always entirely obvious. In a traditional, this is another big difference. In traditional randomized trials, you recruit subjects over some extended period of time. Like you might spend 6 months recruiting for a subject for a study, or even several years. And so one of the differences in cluster randomized trials is that it's possible sometimes to basically recruit or enroll your clusters in a very short period of time. And in the case that I'm going to show you in a minute, the intervention actually began simultaneously across the clusters. And so, as I mentioned, the other big difference of the analysis, the traditional analysis assumes independence between subjects, and in group randomized trials, the analysis needs to account for the dependence between subjects within the same cluster. So now what I'm going to do is I want to move on to the example that was kind of the motivating example for the study about constrained randomization. So a group that I collaborate with was doing a study to improve colorectal cancer screening in primary care practices. And we developed an intervention, and it was aimed at improving the colorectal cancer screening rates within PPRNet. And PPRNet is a network of primary care practices all around the country. There were about, at the time, I think we had about 150 practices in the network. Now, not all of them wanted to participate. We ended up selecting 32 practices to participate. And so when I say improving colorectal cancer screening, that included, at the time, colonoscopy, sigmoidoscopy, and fecal occult blood testing. And so that was basically our primary outcome in the study. And I'm not going to really talk so much about the outcomes and the results of that study. We did publish that, and in the end, it turned out that the intervention helped improve the screening rates to from about 8 to 10% percentage points within the practices. And so the intervention had 3 components. And so as I describe these, you'll get a sense of why we actually randomized at the level of the physician practice. So by audit and feedback, what I mean here is that we audit their electronic health records. We obtain all of their electronic health record data. We generated reports and fed that back to them to give them a sense of how good they were doing at screening for colorectal cancer, among other quality measures of healthcare quality. But really, these are mostly about most of the feedback had to do with prevention for different diseases and outcomes. The intervention also included site visits. So our clinical investigators went to these sites a few times a year to help talk about their data with them, show them where they stood in relation to the other participating practices, and help provide them with any new information about colorectal cancer screening that may have come out in the literature during the study time. So that's what I mean by academic detailing here. And the last component of the intervention involved bringing all of the intervention practices together, so not the control practices, but just the intervention practices, and they could share with each other about their best practices. And so as you can imagine, for screening for colorectal cancer, there are certain barriers that are going to have to be overcome to get your patients to agree to do that. So I want to kind of step back for a minute and pose a hypothetical question for you to consider here. So imagine you're conducting a traditional randomized trial, randomized clinical trial, and you're going to enroll N subjects, and you're going to divide them or randomize them into 2 groups. However, instead of recruiting the N subjects over time, imagine that all N subjects show up on day 1 of enrollment. They all come at day 1. You enroll all of them, and they all agree to participate. You collect all of their baseline data, and now you're in charge of randomizing them. Now, I understand that's not how things traditionally happen when we do studies. But think about that. If all of your study subjects showed up on day 1, and you were in charge of randomizing them, how would you proceed? Would you do anything special? Would you try to incorporate their baseline characteristics into your randomization process? Would your answer depend on your sample size? And I ask this question because this is the kind of situation that we have with the group randomized trial, because now all of the patients aren't showing up on day one, but all of the practices are showing up on day one. Actually, we have them before day one, but the intervention is all going to happen at the same time, and we have all of the baseline data that we're interested in. And so when we were planning this study, it was the family medicine physician, the principal investigator in charge, really wanted to help. He wanted to be a part of this randomization process, and we kind of worked together to come up with some solutions. And so the other thing I want you to take away from this kind of example is that this is one of those opportunities where it's it's a time to think about how do we about collaboration instead of consultation. And it's this example in particular is I think a good example of team science. So it incorporated people with expertise in family medicine, internal medicine, nursing, health information technology, and biostatistics. And this, I think I actually left out some important groups here. So these are the investigators that were on the grant had this expertise, but we also relied a lot on the physicians within the practices, and sorry, not just the physicians, but the whole team within the clinical team within the practices. So we had nurses, and we had even upfront office personnel who helped essentially design the to improve the screening within their sites. And so in the end, we ended up with 4 different papers from this project. We actually had 2 qualitative papers with the nurse as the lead author. So she wasn't the PI, but she ended up with 2 first author publications. I actually got to be second author on one of those publications. The PI tended to be last on those publications. On our primary paper, the PI was the first author, but I got to be the last because the analysis ended up being extremely complicated, and because I had been working with them, I was given that opportunity. But for me, most importantly, out of this study, I ended up I was the lead author on this methods paper, which I'm kind of going to walk through in a minute, and the PI was last. So we ended up with 4 papers. We probably could have published a few more as well, but the point was we shared in first authorship, we shared in last authorship. But more importantly, because of our success in this type of study, we ended up getting, we have at least 5 grants together after this one. So again, I think I mentioned we have 32 practices that agreed to participate in this group randomized trial. I should also mention, if you're ever helping to design a study like this and write a grant to get funding, you want to get letters of support from all the participating sites if you can. The reviewers are almost always demand that, and several times we were not able to get them on our first round of on our first grant submission, but we ended up getting them for the second one. But I can't even think of a time when we didn't have the letters of support from the individual sites. So the PI, came to me. He said, "You know what? I really want to balance these groups on some factors that we need to think about." And at first, I thought this was ridiculous, but this is where he came to me and he said, "Okay, I want to balance by geographic region." So remember, these practices were spread around all 32 practices were spread around the country. We had some in the East, some in the South, some in the Midwest, some in the West. Some of the states involved had actually mandated insurance coverage for colorectal cancer screening. So we thought that it was possible that factor may influence the outcomes in those states. We also thought perhaps we might need to consider not stratifying, but trying to balance on baseline colorectal cancer screening. So we had some low performers, medium performers, and high performers. Now, it didn't end there. They also wanted to balance on prior experience with working on research projects within PPRNet. You might say, what does that matter? Well, the practices who had participated before were kind of familiar with our intervention, and they tended to be kind of have better performance over time than the new practices. They also said, how about specialty, family medicine versus internal medicine? I think the internal medicine physicians thought they were going to do a better job at this. Number of providers is actually a very important factor to consider, not so much because of the absolute number, but because number of providers is a good, it's a good marker of how large the practice is. And if you've ever tried to do an intervention where you make change, you get the participants to change their behavior, you recognize it's a lot easier to get a few providers to make changes as opposed to getting, a practice with say 30 providers. So the smaller ones are kind of easier to help change. We also had 2 practices that were participating that were residency programs, and these had large numbers of providers and large numbers of very junior providers. So the first thing you think about is, well, there's 7 factors. Is that even, I don't even, is that even possible to balance on all of those things? How do we do that? Why don't, so the first thought was, well, is it possible just to use stratified randomization? And my conclusion was it was basically impossible to do that with 7 balancing factors. So with 7 factors, if we said each factor just had two categories, there would be at least 2 to the 7th strata. Now, some of our factors like geography actually had 4 strata. So this is at a minimum here. But if we had 2 to the 7th strata, we would almost surely that most strata would have almost surely 0 or 1 practices in them. So then it would be impossible to allocate half to the treatment group and half to the control group. Now, some people argue that there are such things called a valid randomization scheme. And basically, you want to make sure that every randomization unit has, or in our case, every physician office or clinic had an equal chance of being assigned to each group, assuming you're doing 1-to-1 allocation, which we were. And I believe that our technique does this just fine. Now, it's also argued that every pair of clusters has the same probability of being assigned to the same cluster. And this would be on, this is a little harder to ensure, and it's something I'm still thinking about. So here's the question. How many possible ways could we randomize n clusters into 2 groups? So think about that for a minute. Answer is choose n divided by 2. That's if n is even. So if you have 32 practices, the answer is 32 choose 16. Or the way you would write that out is n factorial over n divided by 2 factorial, n divided by 2 factorial. Is that a lot? And the answer is yes. So in our case, 32 choose 16 gives you over 600 million ways to randomize the practices. And so simply enumerating all those possible ways can be impractical. In our case, I'm not a great programmer. I'm kind of an inefficient programmer, and that was just something I wasn't going to be able to do in a short amount of time. It might have been possible to enumerate them all, but then to figure out whether they were valid or kind of good or not was going to be difficult. So here's our simple. This is the solution that I came up with. Now, you may look at this algorithm and just say this is silly, or it's too basic. But this is what I call kind of my brute force way of handling a problem like this. Well, so I took the 32 practices and put them into two groups of 16. And each time I did this, I'm going to call that a randomization scheme. So I randomly split them up into a single scheme and say, well, okay, now that I've allocated them, how do they balance on all those 7 factors that I listed? And if they were sufficiently balanced on all the criteria, I kind of saved that for later. And then what I did was I repeated that until I collected enough balanced randomization schemes. And when I did this the first time, I let my program run overnight, and it ran. I think it did about 30 or 40,000 randomizations, and we ended up with about 100 that looked balanced on all of our factors of interest. But I would also say if you do this process and you don't have enough valid, fully balanced schemes, you're going to have to kind of relax your balancing criteria. So what do we mean by balancing criteria? Well, let me back up a few slides here. So for example, this last factor here, residency program, we had 2 practices that were residency practices. So we wanted to ensure that one of them went into the treatment group and one of them went into the control group. And if that happened, then we would consider it balanced on factor 7. And we did that for all of the other factors as well. But what I'm proposing is you do this until you get enough randomization schemes that are balanced, and then you select one of those at random. And I do have a pretty simple SAS program. It's going to require a little modification for your particular situation if you're interested. So if you're interested in that algorithm, I can email it to you and kind of walk you through how to do it. So the question, did it work? Well, here are our 16 control practices and 16 intervention practices, and here's our first factor. So geographic region. So if you see here, I had four control practices and 3 in the intervention group. So a total of 7 were in the East, and they were split 4 and 3. So we decided if there was an odd number in a certain category, that it could differ by at most 1 unit. So 4 and 3 would be okay, but we would not accept 5 and 2. So in the South, we had 2 and 3. In the Midwest, we had 5 and 5. And in the West, we had 5 and 5. And we actually, for the ones, so in this case, like the West here, we had a total of 10 practices in the West that we split into the 2 groups. We wanted 5 to be in each one, and 4 and 6 I don't believe was going to be acceptable. So here are other factors. Here's the second factor, the state mandated screening for the insurance payment for or the mandate that you had to cover the colorectal cancer screening. That was split evenly. Here's the baseline colorectal cancer screening performance. Again, split here, so 5 and 6, 5 and 5, 6 and 5. The past network research experience was split. Most of the practices had no experience, but we did have 8 that were experienced, so we split them 4 and 4. And again, this is all done simultaneously. And so what I'm saying happens here is that in a sense, we are balanced on the margins. For each of these factors, we're balanced on the margins. So we're not balanced on on combinations of factors, but we are balanced on all the margins. Here's our residency program. So remember I said we had 2 practices, and one was in the control group and one was in the intervention group. We also had some other factors but we didn't balance on these. But interestingly, they turned out to be pretty well balanced. So colorectal cancer screening is recommended for patients over 50 years old, or at least it was at the time. I think now there's an upper limit on that. I think it's 85 years old now. You don't want to be screening people who are 85, over 85. But the simple number of patients, these are medians and interquartile ranges, so practice medians. So the numbers in each group were pretty similar. This is kind of our baseline rate, the percent of patients who were already up to date with colorectal cancer screening, so about 50% in each group at baseline. The mean age among patients at baseline was pretty similar between the two groups. And this is basically the gender makeup. So the percent of patients over 50 years old who are male. So a little over 40% in each group. So again, these were factors that we weren't balancing on, but in the end, they turned out to be balanced on these as well. So I would say there are some limitations to this type of approach. If combinations of balancing factors have an interactive effect on the outcome, then the strategy could lead to biased estimates. So for example, maybe like if you were thinking back to the traditional randomized clinical trial, if you're trying to stratify on gender and race, if there's an interactive effect between gender and race on your outcome, this is the kind of thing that would be missed in this in our approach. And ultimately, the analyses may need to be adjusted due to a smaller theoretical randomization space. And this is a little more, I'd say here's where some future work could occur. So I don't know how often any of you have actually used a permutation or something called a randomization test to analyze data from a randomized controlled trial, but they involve constructing the distribution of all possible intervention effects under the null hypothesis. And when you start doing constrained randomization, the number of all possible intervention effects becomes significantly smaller than if you assumed a simple randomization scheme. So I think there's some other work to be done. I didn't really thoroughly vet what is the impact on type 1 and type 2 errors. And I've talked about this with some of my colleagues, but how, what are some appropriate ways to adjust for any constraints that are imposed? And if so, are there any that are considered best under certain situations? So one of my answers to some of the, to people that are complaining that I'm overly constraining here, I just say, these are called pragmatic trials for a reason. There's nothing perfect that in these kind of situations, but sometimes we just need a simple tool to get the job done, and that's kind of what I did here. I just, we generate the randomization schemes and see if they work. If they work, that's great. Use one of them. Nothing too complicated. So I would like to acknowledge the PPRNet research team that I've been a part of for most of my career. So Steve Ornstein was the PI on our early grants. He's the family medicine physician. Lynn Nemeth is the nurse that I mentioned. Kara Litfin is internal medicine. Ruth Jenkins is a health information specialist. Andrea Wessel is a PharmD, and we have an MPH, Vanessa Congdon as well. And the work in colorectal cancer was funded by an NCI grant. And of course, I'd like to acknowledge our CTSA grant and of course the Delaware CTR grant as well. So the top reference here just goes into a little more detail about the process, the algorithm that I laid out here. One more quick lesson that I think it was interesting from this project, which is, so I published this paper in Contemporary Clinical Trials. When I first submitted it, I got a pretty quick rejection letter from them. And I was about to move on, and then I noticed something, that they had a section called brief reports. And I emailed the editor back and I said, how about reconsider what you just, publishing this? Why don't you think about it for a brief report? And he took about a day, the editor did, and said, you know what, you're right, let's do that. And so he sent it back out for review, and next thing you know, it was accepted. So it's a brief report, just walking through the algorithm that I just walked through with you today. There's also here's a nice paper by Dickinson and others called Pragmatic Cluster Randomized Trials Using Covariate Constrained Randomization, a Method for Practice-Based Research Networks. And one of the novel things they did is if you notice, in my algorithm, we are only considering categorical factors, and they use continuous factors as well in their approach. And because of that, theirs, I would say, is much more complicated, but it might be relevant for this situation you're in. And there's also a nice paper that just kind of talks about some kind of pros and cons of constrained randomization for group randomized trials by Moulton in Clinical Trials Journal. So thank you for your attention. I may happen to answer any questions you may have.
Well,
Go ahead.
oh, I can go ahead. Okay. Do you have some notion of how many permutations or combinations you need to randomly select one? You mentioned you had 100 to select from.
I don't know that there's there's not a right answer to that. I think the more the better. So I think I said there were 600 million ways to have randomized the 32 practices. Ideally, I would have liked to have been able to kind of go through all 600 million and pick out all the ones where there was balance. Now there wouldn't, all of those wouldn't have been balanced, but maybe if I had been able to go through all 600 million, tens of thousands would have been balanced. And in that case, I think that would have been a better way of doing it. I think I was only able to, my program was, after running for a day or two, it went through about 30 or 40,000, and that was, but again, that was kind of due to my inefficient programming. So I think the more the better, kind of provides you the better theoretical base for your essentially your p-value, the p-values you end up with at the end.
So in that regard, how do you pick the best one? When you're going to roll at the end of the day, you're only going to use one.
Well, yeah. So I don't know that if they're all balanced, you set up some criteria on what you consider acceptable, and of those that are acceptable, you just randomly pick one. I don't think you say one is better than the other.
So how did you analyze the data, and what type of statistics did you use?
I ended up using a set of mixed models with I think I had 2 levels of clustering, because I had some repeated data on patients over time. I had repeated data on practices over time. Those were some complicated covariance structures to specify. I think we also did I think I may have done some non-parametric tests on the practice level data as well. So we kind of came at it from a few different angles. There's always a lot of different ways to look at this type of data, and it's good to pre-specify it up front as well. And I'll just add, so you said, how do I analyze? And the key thing is to account for that practice level variable as a as a random effect in your model, or using some type of GE model where you're controlling for that practice clustering.
Paul, I have a question. When you got your 100 options, for every option in there, do you include its mirror image, like flipping the assignments as an option? Like if a cluster, one particular cluster was A and another was B, and there was 16 and 16, then
Right.
the opposites, B and A, would also be an option.
Yeah,
the number of options.
I think I picked a I think actually we picked a scheme, and then where we did balance, and then we randomly said, okay, wait, which group is going to get the intervention and which is going to get the control. So there was I guess 2 levels of randomization there. So that accounted for the fact. So the 100 were 100 unique strategies, but each of those had 2 possibilities.
Right.
In fact, I think it was kind of fun, and we did it. I did it with the other all the other investigators, kind of, you know, because they're kind of rooting for certain practices to be in the intervention and certain to be in the control, you know. So, and we ended up doing the randomization together, and you know, it turned out fine. So.
I like the idea. With patient trials, there's a similar approach. I think it's called minimization, where as patients come in, the idea is to try to balance the margins. And I think that kind of randomization or allocation is frowned upon because patients do not have that possibility, equal probability of being in each treatment. But you overcame that by listing a bunch of options to start with and then randomly selecting one of those, so that every cluster did have the equal probability of being in either treatment assignment.
Yeah, that's a good point. Yeah, so when you say minimization, what you're saying they're minimizing some global statistic that reflects their covariates, and I guess we're minimizing some of that as well, but it's not preventing any of the practices from being in the. Each practice still had a 50-50 chance of being in the intervention or control, and what you're describing, it would change the individual's probability.
So it looked like it works for you, but it really just, its counterpart for a patient trial just doesn't work.
Unless if you had all of your patients at once, which I talked to somebody here who does a lot of trials, and he said he had one like that recently, and there you might minimize. You could adapt this to that situation where you could minimize some global statistic, and then randomly pick a group for them to be in. I think it's possible, but it's not in the traditional sense of minimization.
I have a question. Hi, Paul. I have a question. Is there like some sort of magic number or some sort of large number of observations or people in the study where you wouldn't have to worry about any kind of stratification? You could just divvy them up one by one into 2 groups and you would be okay?
Probably. It's kind of like, can you imagine doing a clinical trial where they don't want to stratify on something? Somebody, usually the PI is going to want to stratify on something, or so if you only had, say, 1 or 2 factors that you really wanted to stratify on, then or even if you didn't really want to stratify, then I think the stratification process or the constrained randomization process could be putting some limits on your work that are unnecessary. So I don't know the number that you would want, but I think with 32 we were probably close to that limit. So maybe, I don't know, if you had 50 groups you're randomizing, you probably wouldn't need to go through this process.
Well, yeah, in mega trials, not cluster randomization, but just mega trials, very often there's no stratification, because the reason for stratification is to achieve balance, and when you have 40,000 patients, your chances of balance are very good. So stratification works better when you have relatively small sample sizes to assure balance.
Good point. Anything else?
Great. Thank you so much.
Great talk.
Thank you, Paul.
Very
Thank you.
unique method. Thanks.
Very interesting.
All right, thanks so much.